Okay, so last time we had class, we talked about position and velocity and acceleration functions. Remember that velocity was the derivative of position and acceleration was the derivative of velocity. And so we are now going to play a little game. So the warm-up is going to be a bunch of different hints. Obviously, I'm just working them out here, but if you want to pause it and do it before me, you should do that. But it says find the first derivative of y, and we're being told that y is ax squared plus bx plus c. So if you use the power rule and apply that to this function, 2 times a gives you 2ax plus b as that first derivative. And then we want to find the second derivative of y. So again, use the power rule. Derivative of that x term there is just going to be 2a, and derivative of a constant term b is just going to be nothing. It's going to go away. So we get the first derivative is 2ax, and the 2ax plus b, and the second derivative is just 2a. So notice that this times that became our second derivative of this quadratic function. That's going to be key in a minute. So here I'm telling you that the average acceleration due to gravity on Earth is roughly the constant function a of t equals negative 9.8 meters per second squared. The challenge is, can you write the equation for the height of an object dropped from 25 meters? The height function h of t is a standard form quadratic function, so we know it's going to be, I'll write it as in blue, h of t equals ax squared plus bx plus c. That is a standard form function. We know that the velocity is the derivative of position, and the acceleration is the derivative of a velocity. So think about what we just did a moment ago. The coefficient of our first thingy here times some a value equaled our acceleration. So if we use that in this function here, we're going to need that a value to can't talk. We're going to need that a value to be half of whatever that third function is, aka the second derivative. And here the second derivative is acceleration, and the acceleration is negative 9.8. So we need that coefficient there to be half of that value, and half of negative 9.8 is negative 4.9. So we get h of t equals negative 4.9 t squared. Now, b of x, think about what's going to happen here. When we take the derivative of this function to get our velocity function, we're going to get v of t. Whoa, that's totally not the right color. We're going to get v of t to equal 2 times a, 2 times negative 4.9. That's going to give us that negative 9.8 that we needed. X plus bx plus c. But think about this. I lied. That's totally wrong. I must be getting tired. Because the derivative of bx is b, and the derivative of c goes away. So think about that negative 9.8x. Negative 9.8x, this is representing our velocity function. So the first bit is just how the velocity is changing from the acceleration. But the plus b, notice we say when an object is dropped, its initial velocity, v naught, is 0. That b is going to represent our initial velocity. If you just drop an object, it's going to start with a velocity of 0, and it's going to build its way up. Unless you were to throw the object, in which case it would start with some v naught value. But in this case, it's just 0. It just goes away because v naught is 0. Okay, so then finally, think about what we need for that c value then, because we need to somehow start this object up high. It was 25 feet in the air, so that last term there is just going to end up being the initial height. So c is the initial height, b is the initial velocity, and a is half of that acceleration value. So we got this function h of t equals negative 4.9 t squared plus 25. More generally speaking, the generic formula for the height of an object is negative 4.9 t squared plus the initial velocity times t plus the initial height in meters. Or if you want to do it in feet, you could go negative 16 t squared plus the initial velocity times t plus the initial height again. So you see they're pretty much the same, just different units there. But think about this. Why did we need to take half of that gravitational force, that 9.8? Well, because of the power rule. When we take the derivative here, 1/2, well, I don't know why I'm writing that. When we take the derivative here and multiply there, we get 2 times 1/2, so that goes away, and then you're just left with gravity to the first power plus v naught right there, and that's going to be our velocity function. So we get the 9.8 that we needed. So that's good. Now, here's the thing. If you go to this clip right here, you can see a YouTube video of some dude out in space dropping some stuff. But the point is, all of these formulas that we're just looking at, these are not taking into account the force of friction, air friction. It neglects that. So if we're on the moon, maybe it would be more accurate, but then we'd have different accelerations for gravity. But you get the idea. These are, laboratory scenarios in a vacuum. So let's go back to our equation now, negative 4.9 t squared plus 25. Let's answer these questions. How long does it take the object to fall halfway to the ground? So what I want you to do is I want you to graph this function. Think about what a good window would be. We know that it's starting at 25 and it's going to follow a parabolic shape down. If you drop something from 25 feet up, it's not going to take that long to fall. So probably a window of like 5 would be good, but in this case even like 3 is good enough, I think. Put a Y max of 25, maybe 26 to give yourself a little cushion there, and mins of 0, and we get that function. And we want to know how long does it take the object to fall halfway to the ground. So for this, you should just graph the horizontal line, y equals 12.5, half of the distance, and then do an intersection point, and you will find that t value. So if you do that, you will get 1.597 seconds. And so then let's look at the next question. Whoops. Next question is, how long does it take the object to hit the ground? Well, for that, we want to find this value right here. So you get two options. You can either go second calculate 0, and then do a left bound and a right bound and a guess to give you that value. But what I do is I just graph the line y equals 0, and then I do second calculate intersects, because for me, that's just personally how I prefer to do it. It's quicker. So when you do that, you will get this value of 2.258 seconds. And then finally, the last question, what is the instantaneous velocity at the time of impact? So now we need to find dy over dx for that x value that we found right there. And my advice to you, if you want to be precise, is to do as follows. Once you calculate that value and find that value right there, hit second quit to go to your home screen, hit the X button, and then do the store option and store it as a variable like a, and that will give a that value, but it won't round it at all. It'll keep it precise, because then when you go back to your graph to find that instantaneous velocity, aka the derivative, second calculate option 6 dy dx, then you can type in the value of a. You can do little x equals a to get the precise value of the derivative, negative 22.135. If you're off a little bit, you know why you are. So now the question is, what if we wanted to know what the average velocity was during the fall of that object? How could you do it? Well, think about how you normally would do the average of something. It's not quite going to work like that. So think back to what we've done with secant lines. If you draw the secant line between 2 points, that is going to represent the average slope of the tangent lines between those 2 points. Now, don't be confused that the average velocity is found by using points from the height function, because this is just doing slope for you. H of b is like your y2 minus h of a is your y1 over your x2 minus x1 is calculating the slope of that line. It represents the average. Be careful, do not go to your velocity function and just do, say, v of 0 plus v of, I'll do a again, that's stored value, over 2. That will not get you the correct answer. That is an incorrect average. So notice I went above and beyond and graphed that secant line, but we see that the slope of it, that average velocity, is found by negative 11.06797. And to do that, we get the, think about the y value here is 25 versus the y value there is 0. So we get 25 divided by that a value, which was the x value over here, 2.258. So we took that divided by 2.258, and it should be negative because that's a negative slope, and you get the negative 11.06797. So now here's an extension problem. Find the time t where the average velocity is equal to the instantaneous velocity. So to do this, I would recommend that you graph the derivative function. You can either use the power rule or you can just do n derived to graph it for you. And we need to set the derivative equal to that value that we just found. So what I did is I stored the slope value, that negative 11.067. I stored that as a new variable, and I graphed it as a line, and I found the intersection between that and the derivative function to figure out the x value where the average velocity was equivalent to the instantaneous velocity, 1.129. And then I went ahead and drew a tangent line at that value to show, hey look, these two things are indeed parallel. Remember, we're talking about the slopes. The average velocity is now equal to the instantaneous velocity, aka the slope of that tangent line. Pretty cool. So if you connect this last bit to the problem you did the other day with the police officer pulling you over, well, you were essentially doing this. You were using the mean value theorem. Mean value theorem says if your function is continuous on a closed interval and it's differentiable, then there is a number c, aka a number 1.129 that we found, where the value of the derivative will be equal to the value of that average slope, the slope of the secant line. So when you figured out that average speed on that cop problem, you were finding the average, and because that was the average, the mean value theorem says there's some time in there where you're going that average speed, and since it was above the speed limit, you had to have been speeding.